Hello and welcome back. Today we're going to talk about Chapter 6 on thermal energy, heat, and thermodynamics. Let's get started. So in this lecture we're going to help you understand the following topics: temperature and absolute zero, heat and quantity of heat, the laws of thermodynamics, entropy, specific heat capacity, thermal expansion, and expansion of water. So we're talking about temperature. Temperature is simply a number that corresponds to the warmth or coldness of an object and can be measured by a thermometer. It has no upper limit to it, but it definitely has a lower limit on the lower end. So the thermometer measures temperature by expansion or contraction of a liquid. This is usually either mercury or colored alcohol. And the reading occurs when the thermometer and the object reach thermal equilibrium, meaning they have the same average kinetic energy per particle. Remember that kinetic energy is energy in motion. And infrared thermometers operate by sensing infrared radiation. So this is the scale of temperatures we have, and we see three of them primarily. Of course, we all are familiar with the Fahrenheit scale, where water freezes at 32 degrees and water boils at 212 degrees. But those are not really easy numbers. So we can use the Celsius scale, which came out a little bit later. Celsius scale says 0 is the temperature for freezing water, and 100 degrees is the boiling point for water. So those are more easy numbers. And we use that in science a lot. Not really Fahrenheit very much. Now, a little bit later on, in the 1800s, the Kelvin scale was invented, and this is a derivation of the Celsius scale. We add 273 degrees to everything. So on the Kelvin scale, 273 is the freezing point of water, and 373 is the boiling point of water. And we use this scale because it has absolute zero on it. Absolute zero is the very coldest it can ever get, which no object can ever have. So minus 273 degrees is absolute zero. Now the theory of temperature has topics about kinetic theory of matter and thermal energy. And so kinetic theory, again, the theory of motion, is that matter is made of tiny particles, atoms, or molecules that are always in motion. And the thermal energy says that the total energy, kinetic and potential, of the microscopic particles that make up matter. So again, here's absolute zero. Nothing can get below absolute zero or even get to absolute zero. Although there have been some lab tests done that some particles did get to absolute zero. That is the complete non-motion of the particles. So the lowest temperature limit is minus 273 Celsius, and that's when atoms and molecules have lost all available kinetic energy, and the substance at this temperature cannot get any colder. Well, as the temperature changes of a gas, the volume of the gas changes. And so, absolute zero is the lowest temperature, and the molecules have lost all available kinetic energy. So what is heat? Heat is defined as a flow of thermal energy due to a temperature difference. So the natural direction of heat flow is from a higher temperature down to a lower temperature. So in this experiment, we have 1 liter of water in a left pot, 3 liters in the right pot. Both pots absorb the same quantity of heat, and the temperature increases 3 times as much in the pot with the smaller amount of water. And so heat is energy in transit. It's measured in units of energy, and we call these units of energy joules, as we mentioned before, or calories. We'll get to that in a minute. The calorie is defined as the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. Okay? And you convert that into the metric scale. 4 about 4 joules is equal to 1 calorie. Now, when you talk about energy rating of food or fuel, we actually use the term kilocalorie. And this is the heat needed to change the temperature of 1 kilogram of water by 1 degree Celsius. And this is actually kilocalories that we use in food packaging. When you see on your can of soup, it says it's 300 calories. We really mean 300 kilocalories. The calorie itself is actually a very small number. So, to summarize this, heat is energy in transit. Heat is measured in joules, calories, or calories, the big letter C, meaning kilocalories. There's 1,000 calories in a kilocalorie. So a scientist would measure a peanut releasing 10,000 calories. That's a bit of heat. Now let's talk about the third law of thermodynamics, and that simply says that no system can reach absolute zero. We've seen that. Specific heat capacity, defined as the quantity of heat required to change the temperature of 1 unit of mass into a substance by 1 degree. And so thermal inertia indicates the resistance of the substance to a change in temperature, and sometimes it's called specific heat. So substances can have their own specific heat capacities. An example would be a filling of a hot apple pie, sounds good, and a greater specific heat capacity than the crust. Watery filling has more capacity for storing heat than pie crust. The specific heat of water, we state that it has a higher capacity for storing energy than almost any other substance, and it involves various ways that energy can be absorbed. How does the heat of water affect climate? Well, for the Europeans over here, in addition to warm jet streams in the atmosphere, current in the Atlantic Ocean carries warm water northeast from the Caribbean all the way up to reach the North Atlantic Ocean. This energy release is carried by the west winds over the European continent. Thermal expansion is due to the temperature of a substance. Molecules will jiggle faster and move farther apart. And when these substances expand when heated and contract when cooled. So examples of that would be railroad tracks closely laid in on winter days, expanding and buckling in the hot summer heat. Or you go over a bridge and you see these joints in the bridge. We'll show that to you in a minute. These or metal lids on glass jars under the hot water will loosen by greater extension of the lid than the jar. And here's that picture, the buckling of the railroad tracks or these joints, and you see these in some bridges, they expand and contract for the different temperatures of the road. Now we can also do this with metal, and a very good example of this that probably used to be in a lot of homes is the bimetallic strip, which is brass and iron welded together. So when the strip is heated, the brass expands more than iron. When it's cooled, the brass contracts more than iron. Due to this behavior, the strip will bend as shown down here. And so this has been used in old thermometers for a house. The thermostat. And so when the bimetallic here coils, the temperature changes and would turn on the electrical circuit or break the electrical circuit. The expansion of water continues to say that water expands when it turns to ice. Ice has open structured crystals like this, resulting from strong bonds at certain angles that will increase its volume. And we'll get into much more about this as we get to chemistry stuff. And this makes the ice less dense than water. Now, when water is between 0 and 4 degrees Celsius, it does not expand. As the temperature of 0 water rises, contraction actually occurs due to melting of ice crystals in the water. and that continues until 4 degrees Celsius. At that temperature, the smallest volume and the greatest density has occurred in the water. And when 0 degree water freezes to become ice, then we have the largest volume and lowest density possible. So finally, cooling of water in the winter becomes more dense and sinks. Continues sinking until the entire pond is 4 degrees Celsius. If you have a lake pond out in a rural area, it will become more dense and the colder water will sink until the entire pond has reached that temperature. Water floats on top and can freeze of the pond. And finally, ice formation lower than 4 degrees can extend down into the base of the pond. And that's it for chapter 6.